So our next question is, why is it that the galaxies differ? Because our best models for galaxy formation suggest that all galaxies begin their lives in the same basic way, right? That's what we have. All galaxies begin their lives right, with gravity pulling matter into a patch of the universe that was slightly denser than its surroundings, and then that patch contracted onto a proto galactic cloud. So basically, right, in the same the protogalactic cloud, right? The same basic way. And then from that point onward, and it kind of the young one, the young galaxies. You kind of see something is contracted, but then at some point it was a split, right? We end up with some galaxies that have disks and some, right? These are with disks, and these have no disks, right? And also remember, the spirals have disks that are gas rich, and then these elliptical galaxies, not much gas at all. It's all locked up in old stars, right? Those low mass, red, kind of cold-ish stars that turn that hydrogen into helium for like forever. So they're different. And so the question is, right, how is it that they ended up in the different types that we see today, right? So today we see different types. Why? Right? Okay, well, we do have some ideas, and our model suggests two general possibilities. And it's either that maybe there was something different in the way they began, right? There were maybe some slightly different conditions in their protogalactic clouds, or the galaxies might have begun their lives very similarly, but later there were some changes, maybe due to interactions with other galaxies. So, one possibility, maybe different conditions in the protogalactic clouds. So let's look at what could have been different. One idea is that the spin was different. Slower in this case, and then faster in this case, right? So if it's faster, then the disk settles faster as well, settles or forms faster. However, if it's very little spin, then there is basically no angular momentum and the gas does not form. So gas does not form a disk, and we end up with elliptical galaxy in this case, and in this case spiral. So angular momentum plays a role, or the spin, right? The spin could be one idea. Now the other idea was the density of gas in the protogalactic cloud. So what's the idea? We have a dense protogalactic cloud. What's going to happen? If it's dense, the gravity will win, and so stars form before the galaxy or the gas that forms stars settles into a disk. And so that's going to end up as an elliptical galaxy. But if the gas is less dense, so dense here, and here is less dense, and then gas does not form stars as fast, and gas has time to settle into a disk, and we end up with the spiral galaxy, right? Okay, and it turns out we do have some observational evidence for the fact that some very distant red elliptical galaxies, so if they're very distant, that is, and I can tell you especially this particular red elliptical galaxy sent light to us when the universe, we were able to calculate that, was only about 800 million years old, right? Okay, so we do have evidence for these kind of things, right? The red elliptical galaxies that do support this idea that most of their stars form very early in the history of the universe. So that means stars in this galaxy are very old, right? There are basically no new stars, and I'm using blue because the new stars, the ones that we would be able to see now if they were forming now, we know we live very fast, and so we know they would have been the massive stars that were hot and therefore emitting the blue light. So no new stars are forming now in this type of galaxy. So we do have evidence that maybe that scenario might work as well in both of the scenarios. Either the density might play a role, or the spin of the protogalactic cloud might play a role. However, these scenarios actually ignore one key fact, and that is that the galaxies actually rarely evolve in perfect relation. And so because of that, we must consider the effects of collisions. Turns out galaxies are pretty close to one another. Basically, the size of the galaxies is quite comparable to the distances between them, which you might recall that's not to say about the stars themselves. Remember when we scaled the solar system, in which the sun became the size of a grapefruit. Then the nearest star within our galaxy was like another grapefruit that was just a few thousand kilometers away. So huge distance compared to the size of the stars as well. And so the collisions between stars are extremely rare. I'm just going to take a note of that. Collisions between stars are extremely rare. But collisions between galaxies, and especially in the past, early in the history of the universe, they were very likely. And so, therefore, frequent. And I'll note here, especially in the past. Remember, this universe is expanding, and so, this whole region in which galaxies exist was much smaller in the past, and therefore galaxies were even closer together, right? So collisions between galaxies are inevitable. And we actually do have evidence for these kind of collisions. This is an example here, okay? We do catch snapshots in the process of collisions, and that this is just one of them. What do we have here? This is, if you're curious, this is called NGC. So we have 4038 and 4039. There are two galaxies here caught in the act of dancing with one another pretty closely, right? So they're interacting gravitationally, and you see how, thanks to that interaction, the entire morphology of the stars was disrupted, and is this vast tidal tails that have been created in this process. So the shapes of these colliding galaxies are going to be distorted by the way the gravity of the gas in the disks of these galaxies is going to act upon all that matter, especially the gas. So an important note, actually, you see here lots of emission nebulae. This is where a lot of star formation happens. So when we have a lot of gas that is bunched up together by these kind of collisions, gravity actually gets a boost, and the so-called starbursts take place in these systems. So do we have any evidence for that? Well, these are a few examples of some of the oldest galaxies observed with the Hubble Space Telescope. So you see, it basically took light more than 10 billion years to arrive to us from these systems. And if just looking at them, none of them actually show, some good they do not look either like spirals or elliptical galaxies, like what we see as being the common type in the present day universe. And instead they appear to be undergoing collisions. They are violently disturbed in shape, right? So no prominent disk or spheroidal component. And so, yeah, this is a pretty good support for the argument that collisions must have been pretty frequent, especially in the beginning of the universe. So this is the beginning, and long time ago, plus 10 billion years, and we arrive at today. Oh, don't like that. Let's try again. There you go. And in case you wonder, we do have people who are working on trying to simulate how these kind of collisions happen. So these are basically several stages. In computer simulations, it's actually a supercomputer. Of simulations of collisions of two spiral galaxies. So these are two spirals. They have their first encounter here, and that first encounter obviously is going to start disturbing the morphologies or the shapes of those galaxies, and they send them in orbits around each other. Now, as the collision continues, much of the gas in the disk of each galaxy collapses towards the center. So, gas driven towards center, and as we will see later on, that contributes to basically feeding the supermassive black holes in the centers of those galaxies, as we believe many of the massive galaxies actually have supermassive black holes, just like what we've seen evidence for in the center of our own Milky Way. And then say second or later stage encounter, and gravitational forces between the two galaxies tear up even more the disks of those galaxies, and they create those tidal tails of stars that they don't live in a disk anymore, and eventually the two centers approach one another. Centers are going to collapse and form a single elliptical galaxy. Most often that is the end result of a collision like this, an elliptical galaxy, and in this case is surrounded by debris. Okay, any more evidence kind of things? Look at this one. These are basically shells of stars. You see them? Observed around some elliptical galaxies that are probably that's the best explanation we have so far, the remains of past collisions. So this is a pretty massive, another massive elliptical galaxy. And here's another example of a massive elliptical. So this image shows central dominant galaxy. So this is in a cluster of galaxy, and the name of that cluster is actually a Bell 3827, in case you want to look it up and see more or other images of this. And it's possible that this galaxy has been growing by consuming smaller galaxies that have collided with it, because actually what we see in the very center of these galaxies are some bright clumps of stars that we believe once were centers of smaller galaxies. So that big galaxy created the dwarf galaxies that existed around this huge galaxy. And we do have evidence for this kind of things actually in the halo of our own Milky Way. We do find evidence, some remnants of some other dwarfs that might have existed in the past, but they were basically eaten by our own galaxy, which had greater gravitational potential in indulging, snacking around the matter that existed there. All right. So maybe some other thing that we see here. There are these blue streaks of light, right? So that encircle the central galaxy. They actually are light coming from a much more distant galaxy, which has been distorted. The light has been distorted by the phenomenon called gravitational lensing. Basically, the mass of this elliptical galaxy acts as a lens, and it modifies the light. It bends the light that's coming from that foreground galaxy into some arcs of light. This is what we see here as the blue streaks. I don't think we're going to have much time to talk about this phenomenon. All right, and one more thing. You might have wondered, does this, gas cycle or, star cycle that we talked about when we looked into things that happen in our own galaxy, does that happen in all of the galaxies, and does that happen fairly similarly, right? Is that cycle happening steadily, and slowly, like in the Milky Way, or or not, or actually, as we see in these examples, rather furiously, just like we see in this what we call starburst galaxies. So these are some amazing pictures of galaxies that form stars at rates, at very high rates. and actually we can quantify that about 100 times faster and more efficient than, say, Milky Way does it. All right. So what we witness in these images of these star-forming starburst galaxies, we see the galactic winds. These are spectacular phenomena, and what what we see here is the intensity of the supernova explosions, right? And actually, if we had some, an image, and you're probably going to see that in some of the examples or questions in the Mastering Astronomy. We, an X-ray image would reveal, some basically X-ray sources, which are accretion disks around black holes, which, remember, are the remnants of high mass stars, which leave very fast, right? So they basically, in astronomical times, it's just a few tens of thousands or up to just a few millions of years, which is a very, very short time in astronomical for astronomical scales. These stars lived and died, so it just happened now. So that's why we actually get to observe these things. And so the supernovae explosions left those black holes behind, and if they live in binary systems, they are going to start accreting from their companions, and actually they are there. So as I said, an X-ray image of this particular starburst galaxy reveals those things in the very center of the galaxy. Now, another interesting thing is that these winds and this, so we have winds here, are strong enough, right? They are basically at the scale of the galaxy itself. While this, for example, is a small galaxy, this would be a kind of a dwarf-ish galaxy, small one, so not as strong of a gravity, right? Then the supernovae will drive away most of its gas, and it's going to, that galaxy is going to have to wait for a while for that gas to settle back into the galaxy, and eventually maybe start forming new stars. But actually sometimes those galactic winds can disrupt the whole galaxy so much that maybe actually destroys the galaxy as it was, and some other things might form out of it. So yeah, anyway, interesting and exotic phenomena that happen out there. But these things that we see, just another very important note, these these can be caused by collisions, right? So and they actually are only temporary stages in the galaxy evolution. And it's possible that some galaxies go through some of these stages, and some just don't. Some, they, especially if they live in isolated environments, they just have a kind of a secular evolution, and maybe they don't go through a starburst phase like galaxies that we see in these beautiful images.